Hi everyone. Today I'm going to introduce Hyperscan, a fast multi-pattern Regex matcher for modern CPUs. And this is joint work between Intel and KAIST. As we know, deep packet inspection is the key functionality in the Layer 7 networking applications. And the Regex expression matching is at the core of DPI. But we face big problems. The record matching performance is slow, and it has become the major performance bottleneck for DPI applications. To solve these issues, the current best practice is called the prefilter-based pattern matching. So basically, it is a two-stage design. It will first go through the multi-stream matching, where the users can pick up the string keywords from the corresponding regex pattern and doing a multi-string matching. After we find the string matches, then we can trigger the corresponding more complex regex matching. But there are problems with the current best practice. First, usually, the string keywords may be improperly manually pick up from the regex pattern, and it may be very easy to match and frequently trigger unnecessary expensive regex matching. And also, this approach will cause some redundant string matching problems. I will give an example here. As we know, we'll first apply a string matching as a filter, as the string matching is usually several orders magnitude faster than regex matching, and we will process this input until we find the keyword that we pick from the regex pattern. Then we can trigger the corresponding regex matching. And the regex matching has to go through the input from the start to the end again. And this process will trigger a duplicate matching of the string keyword and waste the CPU cycles. And secondly, in this process, we usually match a whole complex regex that is usually converted to a slow NFA matching. We can also look at the algorithm level. Both the string matching algorithm and the regex matching algorithm is quite slow in our current practice. Here we summarize the issues here. We solved the first problem with novel regex decomposition, and we solved the second problem with the SIMD-based pattern matching. After we apply the solutions, the performance improvement is substantial. For the real-world application Snort, we can achieve a roughly a factor of 9 performance improvement. And also, Hyperscan achieves 3.2 speed up for multi-stream matching and 13.5 speed up for multi-regex matching over the best known state-of-the-art solutions. Hyperscan is a commercial product and has been widely adopted by real-world applications. And it has been deployed by over 40 commercial products globally. It is used by tens of thousands of cloud servers in the data center of Tier 1 cloud service provider. And it is also integrated into 37 open source projects. Okay, so let's move on to the regex decomposition. I will briefly talk about the overall idea of the decomposition-based matching. So we show an example here. We will first decompose this pattern into several indecomposable string components and regex components. And we will make the string matching at the entry point to trigger the corresponding FA components that is, much more complex and expensive than matching the string components. In order to get a match, we have to guarantee all the components has been matched in the exact order from the original pattern. So we give an example here. We will first apply the string matching until we find the string components BAR. And then we will try to check if we need to trigger the neighboring FA components. But in this case, we don't have trigger either FA1 or FA0, as we haven't matched the string component 2 in our input. So this process will avoid the duplicate string matching, and also the decomposition will likely to generate much smaller FA components that we can further convert it to a fast DFA matching. And finally, in terms of multi-regex matching, we can decompose multiple patterns into FA components and string components and match all the regex in parallel for the same input string. So after we know, the value of regex decomposition, then how can we atomically decompose a regex? And secondly, after we apply the decomposition, how will it benefit the real-world regex? We will first tackle the first issue, and we address the first issue with a graph-based decomposition. As usually, the text-to decomposition for the regex is tricky because the string keyword can often hidden behind the complex regex syntax. So here, we deliver a graph structure analysis that gives much more insights about how to do the decomposition. We will first convert the regex into the corresponding NFA graph structure. Then we apply 3 different analyses to decompose this graph into multiple string components and FA components. I will briefly describe the graph structure analysis here, and please refer to our paper for more details. So first, we will introduce the dominant path analysis. Basically, this analysis will discover a single dominant path, and every transition from the start state to the accept state has go through this single path, and we can convert the single path into the string component. So if the dominant path fails, we can further apply the dominant region analysis, and so we can extend the discovery to a region of string keywords. What if the above 2 analyses both fail? Then we can further apply a network flow analysis targeting at the generic graph structure. So basically, it will run max flow minimum cut algorithm to find a minimum cut set of the graph edges and then divide graph into multiple components. So once we have the 3 different graph analyses, so how can they benefit the real-world regex? We evaluate the Snort and Suricata rule sets here, and as we can see from this table, the majority of the regex rows are decomposable by the 3 different graph analyses. And also, the dominant path analysis is quite effective. It achieves a very high decomposition rate. Further, we are going to show the quality of the automatically extracted keywords. As we know, the Snort usually manually pick up the string keywords that are likely to match and triggers a lot of expensive regex matching process. With our decomposition-based approach, it can significantly reduce the number of invocations of the regex matching. As we can see from this graph, we can achieve up to 700 times smaller number of regex invocation. So we adjust the decomposition issues, then we will move on with the individual pattern matching algorithms. Here, we basically use the CMD-based instruction to accelerate the pattern matching algorithms. As we know, the modern CPUs already support the CMD instruction to improve the data level parallelism. And their existing research shows CMD instructions can increase the pattern matching performance by a factor of 2 in the database use case. So here the goal will be using the CMD instructions to accelerate both the multi-stream matching and the FA matching. We'll first visit the multi-stream matching algorithm here. So this is a two-stage design. First, we will apply a multi-stream shift-order matching. Basically, this is a proxy matching that can find the candidate input. Then we can further feed the candidate input into the verification stage and with the further hashing and exact match. So basically, we will leverage the CMD instructions for the extended shift-order matching stage. And this extended shift-order matching is basically based on a classic matching algorithm called the shift-order matching. I will briefly talk about it here. So in this algorithm, we need to generate a shift mask for all the characters and encode the shift mask based on the position where this character appears in the stream pattern. And once we have the shift masks, in the runtime, we can, for each input character, we can do a left shift by 1 bit of the state mask, and then doing an OR operation with the shift mask of the current input character. And we can repeat this process until we find a valid match. This algorithm has its limitations. First, it is single match only. Second, it cannot benefit from CMD instructions. So we're further to extend the original classic algorithm to support multi-matching. So the basic idea is we would convert the original exact match to an proxy matching with multiple patterns. And we will group multiple patterns into n different distinct buckets. Further, we will extend the shift mask by n times and encode each bit in the shift mask to represent the bucket ID. And the shift mask also stores information for all the stream patterns appear in this bucket. And then we can further apply the CMD acceleration to further improve the overall matching performance. And we will give an example here. So basically, in this example, we will make this shift mask as 128-bit, and we will have 8 different buckets. So in the matching process, we will first pre-shifting the shift mask by a multiple of 8 bits. And then we're doing an OR operation to get the result mask. And this result mask will deliver the matching information to us. This algorithm has 2 advantages. First, the pre-shifting of the shift mask will break the data dependency and increase the instruction per cycle. And secondly, all the shift mask operations will leverage the CMD instructions that substantially improve the performance. So we will move to another topic. It is based on accelerating the FA matching algorithm. As we know, the DFA matching is already fast, and we usually use DFA as much as possible for the FA component matching. but it's often not possible because of the state explosion issue. And the classic interface is slow because we always trigger multiple input memory lookups for each input character. To address these issues, we propose a bit-based interface matching where we represent each state with only one bit and leverage the CMD-based parallel bit operations to quickly compute the next states. And I will leave the details to the paper. If you are interested, you can refer the paper. And actually, Hyperscan has a lot of other subsystems that delivers some optimizations for different subcases, like small string matching, some NFDFA cyclic state acceleration cases, or small size DFA matchings. So I will not cover it here, but you can definitely read the paper for more details. And let's move to the evaluation section. Here, we will first try to evaluate the performance of Hyperscan on string matching and Regex matching by comparing it with the state-of-the-art solutions. And secondly, we will see how Hyperscan performs on real-world application. And the experiment setup, we conduct the experiment on Intel Xiang CPUs to get the single core performance. And we use the Snort and serial cutter rules against the random traffic and the real-world web traffic. Here, we show the multi-string matching performance on Snort rules. And as we can see, we can get up to 3.2 speed up for the random workload compared to the state-of-the-art solution. And also, we can get 2.5 speed up for the real-world traffic. And in terms of Regex matching performance, here, from these two graphs, we can see Hyperscan get at least 1.8 performance improvement in terms of single Regex matching, and at least 6.9 performance improvement over the best node solution. And here we will look at the real-world application performance benefit from Hyperscan. So we take Snort as an example. And we use Hyperscan to replace the string matching and the Regex matching performance for Snort. And we are evaluating the performance with the Snort default rules and the real-world web traffic. And from this graph, after integrating Hyperscan into Snort, the performance increases roughly from 100 megabits per second to 1 gigabits per second. And this is roughly more than 8 times speed up. And in conclusion, Regex matching is at the core of DPI applications. And Hyperscan delivers great performance by leveraging a novel Regex decomposition and a CMD-based multi-streaming matching and NFA matching. And during the evaluation, Hyperscan achieves significant performance boosts for both the string matching and the Regex matching. And finally, Hyperscan delivers a real-world application performance boost by more than 8 times. And finally, we would thank Maybar, Xcore, and Justin for their core contribution to this project. And all our source code is at the GitHub link here. And we strongly encourage you to download the code and have a try. And so thanks for listening. I'll be happy to take questions.
Excuse me. Dodir from UBC. Thanks for the talk. I have 2 questions if you have time. The first one is about the breakdown. So you introduced multiple optimizations, right?
Yeah.
Like multi-string and graph-based. So how much each contributes? Do you have numbers?
I don't have the exact number. So the theory behind the decomposition is the matching of the string matching, it is much, much faster than regex matching. It's like several order of magnitude faster than regex matching. So we will always leverage the string matching to make it as filter and to boost the performance. So in theory, it will be like several orders performance boost. Yeah.
Okay, thanks. I guess I can move on to the second question. So the graph-based optimization you had. So I was wondering about the rule set churn versus that optimization. So you said you loaded Snort, say 10,000 rules, and you do graph-based optimization, right?
Yes.
Now, if I add 10,001 rule, how much time it takes to do that optimization in runtime? Is it like 2 minutes, 2 hours, 10 hours?
I think, so Hyperscan basically consists of 2 stages. One is compile time, and the other is runtime. And in our basic usage, people care more about the performance, the runtime performance, instead of the compile time performance. So, and at least from our evaluation, Hyperscan's compile time performance is usually under 1 second.
Under 1 second?
Yeah. Even for, like tens of thousands of regular expressions, yeah.
Okay, impressive. Thank you.
Yeah.
Okay. I have a question. So my understanding is this is actually a long-running project, and it's actually widely deployed and widely used.
Yeah.
Is that correct?
Yes.
Okay. So given that, can you tell us a little bit about like the experience or the evolution of the system over the years, right? So presumably this is not the first idea, this is not the first incarnation of the system. Can you tell us a little bit more about the experience or the evaluation that's going to be valuable for this community?
Yeah, sure. So I think this project is developed as a startup company. And so for the first version, we are using the pre-filter-based matching as just like the current best practice. So we find this kind of solution is not very friendly to multiple regex matching, as usually we need to convert the regex into NFA components, and this is very slow. And we are not likely to generate a fast DFA matching in terms of large scale matching. And so we are trying to further optimize the pre-filter matching by manually extract more string components and to strongly guard the regex matching. But it is still not optimal enough. Then we're thinking about doing the graph decomposition, and it is a much better solution with smaller FA components with a faster string matching performance, and this will definitely beat the original solution. And after that, I think the framework or the structure of Hyperscan will be a bit mature, and we're looking at the internal organizations of our subsystems. We are looking at more instruction set of the next generation CPUs and how to leverage it for our internal components. And we are also looking at the customer requests about how to make Hyperscan ease of use and increase the usability of Hyperscan. Yeah, so this is basically a long way to go, and Hyperscan really does more than a decade of work. Yeah.
Thank you. Any other questions? Let's thank Xiang once again.